Perfect. So we're here to talk about trend analysis and machine learning in PHP. But quickly, before we kind of get onto that, a quick word on who I am. So my name is Michael Cullum. That is my Twitter handle. I'm going to be up here for the next 40 minutes or so. So if you want to tweet constructive feedback or comments about what I'm talking about or anything else, then feel free to just tweet it at me. I work for a company called Bud. We're a financial tech company, a fintech company that helps connect consumers, people like you and me, to financial services. So whether that's converting money into different currencies or that kind of thing. I'm also the security lead on the Symfony framework, which I'm sure many of you will have heard of. So if any of you are kind of want to come chat to me later about Symfony stuff or security stuff specifically, feel free to come find me. And I'm also part of the core committee on the PHP Fig. PHP Fig is kind of like a standards group for PHP, but a forum for lots of different projects to kind of come together and find solutions to problems. So if any of you want to talk to me about that, then come find me. So I imagine a bunch of you came to this talk, so you're like, oh, machine learning, artificial intelligence, that sounds really cool, right? The thing is, I'm actually not going to talk about artificial intelligence at all, because artificial intelligence is a load of rubbish. And in order to achieve a true artificial intelligence, what you're actually talking about is being able to find a way to replicate a human in a machine. And to do that, I think you need to study the brain, and you need to do a whole load of stuff there, and I think we're a long way off of actually replicating a human in a machine. What I am going to be talking about is machine learning, which is, oh, my clicker's having a bit of fun. What we are going to be talking about is machine learning, how we can teach machines to learn things. They can't understand what they're learning, but they can learn things in order to achieve a sort of series of steps, which we're going to talk through. But before we can talk about how a machine can learn, I think we actually need to focus on what is learning by itself. When we all go to school and have an education, one of the most important things that it's actually you get out of school is not how do tectonic plates work in geography, or what is climate change. What you're actually learning is how to learn. The whole process of education at school is teaching you the skill to acquire other skills. Most of you, I imagine, didn't learn to code when you were at school. But when you had left school, you had the skills to learn new skills, and then you learned to code, for those of you that are developers. So let's have a look at what that but the thing is, that learning process, it's quite hard to describe, and we come out of many years of education learning this one really core aspect, but actually, how do you learn something new? It's quite a hard question to answer. So first of all, you see a cause and effect. This is what I'm hypothesizing the learning process is that you ingest a cause and an effect. You process this in your brain. You add some context, and then you store it into your knowledge base, store it into your brain, into that hard drive up there. So just to talk through an example of what I actually mean by that, if I drop my badge here, that's a cause. Then I observe the effect, which is that it falls to the ground. So cause is I drop it, the effect is it falls to the ground. I process that in my brain. I'm like, okay, it kind of goes through some CPU cycles. I add the context to the situation. I'm on Earth. I'm in this room. I am not dreaming. So I'm adding context to that, and I'm storing that in my brain. I now know that happened. Now, once I've stored that in my brain, then I can start to make predictions. I can use what I have learned. So if I take my badge, I have a cause. I'm going to drop my badge. In my knowledge, I have what happened to me just 2 minutes ago, which is that last time I did this exact same thing in the similar context. I saw it fall to the ground. So I can predict that when I have this cause, which is I drop my badge, then I predict it will fall to the ground. I predicted correctly. Yay, we haven't just lost a sense of gravity. Now, that is essentially the foundation of human intelligence, the ability to learn things so that we can then make predictions. And that's what you spend your entire life doing, is making predictions. That's how intelligence is based, essentially. When I walk outside every day, I predict that the sky is not going to be purple. I predict that my arm is suddenly not going to disappear and appear on the other side of the stage attached to someone else's body. That would be weird. That would be something I haven't seen before. And if you think about this in an academic context, then all we're doing is making hypotheses and predicting things that might happen. But sometimes that changes. For example, I'm predicting that every single time I take a step, I'm just going to move across this stage. But if I was on the moon and I took a step, I might float off into a different direction. Because I haven't learned that, I haven't seen that, I haven't had that experience. And that's why when you're a baby, you're constantly learning these new experiences, learning new things, seeing more causes and effect. The reason as humans that we're more intelligent than a machine is normally just because we've seen more causes and effects happen. So, pick that up. So this is my hypothesis, this is my thing about how the learning process works. We take a cause, we take an effect, we process that, we add it into our brains, into our knowledge base, and then when we see a cause, we process it, and we then predict an effect. Yeah? Sounds simple, right? So let's put this into a couple more sort of situations, but sort of start to take a math spin on it. So when you learn maths or mathematics at school, you kind of get taught 1 + 1 = 2, and 1 + 2 = 3, 2 + 1 = 3, 1 + 3 = 4, 3 + 1 = 4. And therefore, you've got your causes. Your cause is your 1 + 1, and your effect is 2. That's what you're predicting the answer will be. So I've now stored that. That's what I've been taught. I've been taught that very simple set of causes and effects. So then, when I see 3 + 1, my assumption is that the answer is going to be 4, because that's something I've learned down here. 3 + 1 = 4. So I predict that the answer is going to be 4. Now, I might be wrong. I am a human, I'm fallible, and maybe I don't know that you have different bases of numbers. So for example, sometimes if we were running on... Oh, sorry, my clicker's having fun. So sometimes you might predict wrong. If you're talking about different bases of numbers, the answer might actually be 1, 1 here, if you were running on base 3, for example. But that's something new. That's something I haven't learnt yet. And computers suffer from exactly the same problems when they do learning. They might not have just learnt a specific way of doing something, a specific way of handling that input. Now, that was very simple. We were looking at 1 + 1, 1 + 2, 2 + 1, etc. We knew the exact things that we were going to expect as our inputs. And if that was machine learning, it would just be a massive if statement, right? And we all know how to do if statements. A talk on if statements would be very boring, unless it's a talk on if statements by Anthony Ferrara, who does an amazing conference talk on if statements. I'd recommend looking up a video of that. If we to look at multiplication, so this is my training set. This is what I'm learning. So I'm going to see 1x + 3 = 4. And I can see that if I multiply the number that's right by the x by 1, then it resolves that equation. It makes sense. If I do 1x + 3 = 5, and I take the number that's right by the x, the 1, and multiply it by 2, then again it resolves that equation. 1x + 4 = 6. Again, I take 2 as my multiplier, and 2 + 3x, I use 2 as my multiplier. So then I get told x = 10, 1x + 4 = what? And I have to predict something. This is something I haven't seen before. I'm having to adapt what I know, instead of just being able to do a replay. This is no longer an if statement. I've now had to abstract what I've learned into a skill. In this case, it would be 14. But I've learned everything I need to by just knowing that if I take the number next to the x and multiply it by whatever this other value is, 10, then it resolves my equation. And as humans, this is how we learn when we're younger too. So when you're a child, you don't know what's edible and what's not. When you're a child, you quite often eat things that are not edible, and that can be quite a problem if you're a parent. But you also, when you start to learn language and you start to learn sounds and you start to learn to speak. So for example, you might see these objects that look a bit like this, and you would commonly hear people saying eggs around it. And you would see that people eat them, and then you would assume that it is something edible, and that in order to describe it, you would use the word eggs. And then when you then learn to read and write, you would then also learn that these are the letters associated with that word, with that thing. So that is the learning process, and that applies to humans, and I'm hopefully going to show you how we can apply that to machines as well. Machine learning is super simple. It's actually just a 4-step process. Anything simple can be put down into a 4-step process. And we're going to just have a look at those steps now. So step number 1 is to acquire data. This is probably one of the hardest steps in the process, is trying to acquire a data set that is large enough or clean enough for you to use. This might involve, for example, if you're labeling some data, so if you're labeling bank transactions, for example, oh, this one's entertainment, this one's groceries, this one is food and drink, this one is, I don't know, bills, utilities, rent. So you'd have to have that data set. On the other hand, if you're maybe looking at logs, then you need to have been collecting your logs for quite a long time so that you can see some anomalies and you know what those anomalies look like, you know what your normal state looks like. Acquiring data can be really hard, and if there's one thing to take out of this talk, it's go away and start collecting that data now. The earlier you start collecting that data, the easier it will be when you suddenly realize in 2 years' time that you need 2 years of data. Secondly, you train your model. So this is the learning process. If we think back to what we were talking about earlier, you had the learning process and then you had the using it process. So training your model, that's when you're teaching a machine how to learn. It's when you're giving it those equations and it's working out that, okay, I need to use X as the multiplier and all that kind of stuff. Step 3, you ask it a question. You ask your model a question. You know, in the case of my dropping the lanyard thing earlier, I trained it, trained my model when I watched it, and I did the experiment multiple times of dropping it and watching what happened. And then later on, I asked my model, I said, what will happen when I drop my lanyard? Which then leads us on to step 4. I got a predicted answer, which is that it would fall to the ground. So let's jump into all of those different steps. As I said, acquiring data, good luck. I can't really help you out with that one. You just need to go and do it. Training your model. So there are 2 different types of learning that we'll talk about briefly. And they are supervised and unsupervised learning. Just a show of hands, who knows the difference or has heard these terms before? Okay, great. So we'll talk about both. So supervised learning is all about known outcomes. It's where you're giving it a series of data and you are saying that, that something is something. So for example, if we were categorizing bank transactions, I would say this transaction for is food and drink, and this transaction is entertainment, and this transaction is utility bills. But the thing is that in order to do that, I need to know what those outcomes are. I need to be able to tell the model, okay, I want my different things to be utility bills and food and drink and groceries. So you're not really discovering anything. It can also be take quite a lot of time in order to produce that really clean supervised learning set. The supervised set either has to be massive, at which point it becomes really hard to label it, or you need to have a data set which is clean, so there's no mistakes in it, which is quite difficult to achieve. we're going to break this again into two separate subcategories. You have quantitative and you have qualitative data. Quantitative data is where it fits into one of the number of different distinct things. So, for example, this is either food or drink, or it is entertainment. There's no halfway between the two. And then you have qualitative, which is all to do with numbers. So, for example, maybe you're predicting the number of hours it might take you to paint a painting, and depending on the size of the painting, it would take you a different amount of time. So that's all where it's on a sliding scale, and it could be any of the values in between. It's sometimes called continuous data. First of all, we'll have a look at classification. So classification is all about saying that X is Y. So in this example, we've got a series of different talk ratings. Imagine you're rating this talk. And someone said 100, someone said 25, someone said 50, and someone said 40. And in addition to asking them for a talk rating, we also asked them, did they feel like they had a positive experience or a negative experience? And we've then just sort of jotted these down. I've also put this on a graph on the right-hand side. Now, something that we'll discover kind of as we go through this talk is that graphs are incredibly helpful for understanding topics. In this situation, it's quite easy to see where our difference lies. But as we go a bit further, we'll see that actually it can be quite hard to visualize without a graph. Graphs can be really helpful. So I've added some more bits of data to this. And now what I'm going to do is I'm going to train my model. I'm going to say, OK, I now want to be able to ask you the question, did they have a positive experience or a negative experience based on a rating? And we can see that sort of if it was more than 49, then it was positive. If it was less than 49, then it was negative. And that's a really simple thing that we've taught a machine. It would have determined that by itself, and it could then suddenly, we've trained our model, we could then ask it a question and get a predicted answer. But sometimes it's more complicated than that. So in this situation, what we've done is we've given a sample of, I think, about 10 people, 2 tests. Now, half of those people are salespeople, and half of those people are developers. And we've given them 2 tests. We've given them 1 test in sales techniques and 1 test in coding. And what we've done is we've mapped out the various results that they got. So we can see that there was this cluster of black dots up here. I give up with the clicker. We've got this cluster of black dots up here in the top left. And those are people who scored really well on the PHP test, but quite badly on the sales test. And then we have this cluster of white dots in the bottom right-hand corner. And those are people who scored quite well on the sales test, but badly on the coding test. And what we want to do is we want to use this in order to train a model to say that, so it can identify in the future, is this person a salesperson or is it a PHP developer? And from this, there are 3 different lines or 3 different models that it might be able to generate. So first of all, we've got this green line, which we're calling H3, our hypothesis. And in some ways, this is actually a really good line, because on one side of it, you only have the salespeople. So it can say, this person is definitely a salesperson, but on the other side, it was like, I don't know if this person is a salesperson or a PHP developer. On the other hand, we then have this blue line, which we're calling H2. And this also looks really good, right? Because on one side of it, we have all of the PHP developers, and on the other side, we have all of our salespeople. So this is a perfect algorithm, right? The difficulty is if I added another dot here, just a person who scored just here, would we consider them to be a PHP developer or a salesperson? We'd probably consider them to be a PHP developer because they're in the top left quadrant as opposed to the bottom right quadrant. So the ideal classifier and the correct one, which we can see from the graph, is the red line, which basically measures the distance. And we'll actually have a look at how we can do exactly this, generate that line in a minute. So that was classification, where something is one of a binary sort of set of categories. Let's have a look at regression. So in this situation here, we have the price of a series of paintings, and we have the size of a series of paintings. We can see that the price might be $5, $6, $4, $3, and the size, 8.25 centimeters, 10 centimeters, 6.75 centimeters, 5 centimeters. And we've mapped these on a chart. And very conveniently for us, they're in a linear, they're going up in the sort of, they're going as much up as they are across. So we can quite clearly see the relationship as the print is larger, it costs more money. Now, what if I wanted to, I only have $1.50 on me, and I go to the person in the shop and I say, look, I've got $1.50, what size print would you be able to do for that amount of money? And I can use this model to predict the size. So in this case, it would be 2.5. Because that's on our line basically. So that's something again related to classification. So that's saying that's supervised learning because we've given it a series of data and told it that X is Y. But we were able to infer data from any point on this line. So I could also be like, okay, I've got $2 on me. How much would that be? It would probably be about $3.75 centimeters. So that's supervised learning. Now let's have a look at unsupervised learning. And as I kind of mentioned earlier, unsupervised learning is all about discovering brand new things. It's all about being able to say, give a bunch of information to a machine and being like, machine, tell me things about this data. I want to learn. I don't know what I want to know, but I want to know more things. And we can jump into, we're going to have a look at two sort of individual things related to unsupervised learning, association and clustering. So association is all about being able to see how one thing is similar to another thing. And in this instance, we're going to look at a retail example. So from a shop, we have a series of people. We have 8 people who bought 2 items each. And we're looking at this data, and we want to sort of say, okay, well, people who bought this also often bought this. So we can see that so we can see that people who we can see that people who buy socks also often buy underwear. That makes sense. They're similar items. When I go and buy socks, I also often buy underwear. That sounds correct. But then the algorithm is also drawing another assumption, which we all know to be wrong, which is people who buy underwear always buy socks. Now, I don't know about any of you, but I have been to a shop before and I've bought underwear and not bought socks. That is a perfectly valid thing to do. The reason that you and I know that is because we have a much larger data set. We have experienced a lot more, and we've learnt that it's perfectly okay to go and buy one thing without the other. And if we follow this algorithm through a bit more, we'll see some similar situations. For example, we'll see that people who bought suits always buy black shoes, and people who buy black shoes always buy suits. But again, as I know that that's not actually strictly true. Whilst people might commonly buy those items together, they don't have to. We can say the same thing about t-shirts and shorts. So people who buy shorts always buy t-shirts, but people who buy t-shirts often buy shorts. So one of those two is correct, the one about people who buy t-shirts almost always buy shorts, but the other one is incorrect. So we can see the mistakes that it begins to make. And this is why it's really important to have really large data sets, but also appreciate that machines are going to make mistakes. It's like teaching a baby, and babies take years and years and years of growth and learning, and then we go through as children and we continue to learn more about the world. And even once we become adults, we're still learning new things. And machines will make those mistakes too. They're no less infallible than we are. So clustering. I was looking for a definition of clustering when I was trying to originally write this talk, because I think it's quite a hard thing to describe. And most of the explanations were really convoluted. But I found one that I kind of liked. But you kind of have to, it sounds like a whole load of gobbledygook at once, and you kind of have to break it down. So what it says is cluster analysis is a task of grouping a set of objects in such a way that objects in the same group are more similar to each other than those in other groups, which is not helpful. However, if we break this down, we can begin to sort of understand what clustering is. So grouping a set of objects. So we're looking at objects, and we are trying to group them together in some kind of way. And if they are in the same group, then they are more similar to others in that group. So it's all about the similarity between objects that determines where their grouping is. And then we might have a series of different groups. So let's have a look at a diagram. So here we've got two different types of clusters. On the left-hand side, we've got with the reds, the blues, and the greens. And this is actually a much easier set of clustering to look at and determine what's going on, because we can use straight lines. If at any point in anything mathematical, statistical, computer sciencey you can do with straight lines, then do it, because straight lines are really, really simple to deal with. It gets much more complicated when you have to deal with curves and all of that kind of stuff. So we can see in the top left portion, then there's a whole load of reds. In the top right, there's a whole load of blues. And in the bottom, there's a whole load of greens. Great. On the right-hand side, though, we can't do that same straight line stuff, because we've got these reds that are quite clearly all clustered together, because they're all quite close together, and you've got this big gap before you get to the blues. But the reds curve around the blues. It sort of involves it. So we need to essentially say, OK, come up with a different algorithm for that. And we'll look at the actual algorithm behind that cluster in a minute. But yeah, so that's clustering. So if we go back to our 4 stages, we then want to ask it a question and get an answer. Now, I'm sure most of you know how to call a method in PHP with some input, with a parameter, and then echo an output. So that's a simple bit. So let's start to have a look at some of these algorithms. First of all, we're going to look at something called least squares. And least squares is essentially a way of being able to determine a trend and draw a straight line. So when you're at school, you probably had to draw a line of best fit throughout a series of different data points. And you would you'd draw a line, and your teacher would look at it and say, yeah, that looks kind of right. The difference is that a machine can't do that. It can't do something by eye. It can't guess. It has to have an algorithm, a series of steps to get somewhere. So in order for a machine to draw this line, we have to have an algorithm, which we'll have a look at in a sec. So in terms of the maths, who likes maths? OK, who hates maths? OK, you might not enjoy this. So the way that you represent a line in maths is through an equation. And that equation is a plus bx equals y. So let's demystify this a little bit. X and y always stay as x and y. We'll explain why in a minute. A is the point at which the line crosses the y-axis. So in this particular example, the A would be 5, just over here, because that's where it's crossing with the y-axis. So we already know one part of the equation of this line. It would be 5 plus. And then we want the B. And what the B explains is how steep the line is, how much it goes up by how much it goes across. Does that make sense? So the B is called the gradient of the line, how steep it is, and the A is about where it crosses the y-axis. The X and the Y. The point of the X and the Y is that essentially determines where different points are on your line. So I have say that my equation of my line is 5 plus 3x equals y. I would then be able to determine that the point on the line that was at 4x, I could determine the y value by just resolving that equation in my head. I can't remember what the equation was that I used. But say that it was 1 plus 2x equals y, and x was 5, then it would be 1 plus 2 times 5, so 11, equals y. So I can determine the y value from the x value of every point on the line. So how do we work out this line of best fit, this least squares regression line? We know that every point on a graph every point on a line has an x and a y value. We know that we need an equation of a line. We know what that looks like. It looks like a plus bx equals y, and I need to work out what a and b are. So what we do is we move this line an infinite number of times. So we create every possible line there is. And then every single time that we draw that line, we draw a square between every point on our graph and the line, where one point on the square is, one corner of the square is our point, and another corner of the square is on the line. And then what we do is we take the area of all of those squares, add them up, and whichever one has the smallest number once we get to the end is the right line. Now, if that was a bit complicated to follow, I have a demo. So this is just a website that I found that happens to demonstrate this, Satos.io. It's not something I created. Please don't give me any credit for it. So essentially what we're seeing here is hand size is our x, height is our y, and then I have these two roundels which allow me to modify what a and b are. So earlier when I was talking about this first one being the point at which where it changes with the y-axis, you can see that as I change it, it moves the line up and down. So if I make that 20, you can see it will intersect that at 20. And if I just put that back to 0. And then this second variable here, you can see that changes how steep the line is. Now, on the right-hand side, what you can see is all of the different squares. So you can see between every single point, if I just walk over here. So you can see this blue point is one of our points. One of the corners of the square is on the point, and another corner is on the line. You can see this for all of the various different points. Now, on the right-hand side, you can see all the areas of all the squares. And the correct line here, actually, for line of best fit, I believe, is 0 plus 1. But it's actually quite hard to get it. Oh, there we go. No, well, that's as good as we're going to get. But that's essentially how we're trying to find our line of best fit. Now, we can do this in code. And I'm actually going to use a library for this. It's called PHPML. It's under PHP AI as the organization. I'd highly recommend using this library. It's a great way to really quickly get started, and then if you're curious as how the algorithms work under the hood, then you can just jump into the library. It's all PHP code. It's mostly understandable. Having an understanding of how matrices work will help you with a lot of this. But yeah, so let's have a look at some of that code. So in this example, this is, yeah. So we can see, essentially, we just got our boilerplate at the top with our grabbing our autoloader and all of that. We then, on lines 8 and 9, have our data points. So we have 60, 3.1, 61, 3.6. So the samples are our x's, and our targets are our y's. Now, if we go through our four-step machine learning process, what was step number 1? Acquiring data, yeah. So that's line 8 and 9. What was step number 2? Train our model, yeah. So that's so if we look at line 11 and 12, then we're training our model with our samples and targets, essentially our data. What was step number 3? Ask a question, which is what we're doing when we run regression predict. And step number 4, get our answer. Let's try it. Cool. So what we're seeing here is that when we're doing a prediction for 64, they're saying that the point on the line is 4.06, essentially. What you'll notice is that that's roughly between 4 and 4.1. So that matches with our model, right? We can see that we can work out that the line kind of would go through that through 4.0, but a bit above that when it's between 63 and 65 because it's between 4 and 4.1. I could also modify this a little bit. So I can make this 65. Now, when I ran it with 65, what you might have expected to see was 4.1, because I told it that 65 was 4.1. Now, the problem is that if we think back to that graph we saw earlier, the line didn't go through every point. So therefore, the point on the line might not match the data that we were given it. It tried to find the best fit, which means that this is a little bit off. It's an approximation, and that's all it ever will be. It's trying to give you a best guess. But you kind of have to bear in mind that there might be an error margin there. So this one is 4.2, which is actually higher than what we've said here. So 65 is 4.1. But on the other hand, if I try this at the other end of the scale, and I try just running 60, then we'll see that it actually returns 3.3, which is also higher. But if I try 61, oh, then I told it 61 was 3.6, but it's coming out with 3.5, so it's actually lower. And the difference between all of those, if you look to your training data and the numbers that it was giving you, if you added up all the differences, you'd get to 0. It would all balance itself out, which is quite cool. So this is the code. It's in the slides later if you wanted to go and have a look at it. I quite often get asked how this works mathematically, because obviously in PHP you can't just iterate through every possible line combination. The answer is, to be honest, quite complicated. It involves a whole bunch of stuff with matrices. So if you have a background in matrices and you kind of want to understand how this works, this is what you do. And I've got it in the slides more for if you want to go home and research that. But it could be an entire talk in itself as to how that algorithm works mathematically in order to try and find the best solution. But it's an optimization algorithm, essentially. So yeah, as I said, it's in the slides. Feel free to go grab that or chat to me afterwards. So the next algorithm I'm going to talk about is nearest neighbor. So we talked about clustering, and this is the data that we have. So we have a series of blue points, green points, and red points. And we want to be able to say, okay, I have a brand new point, and it is here. And I want to be able to say, is that going to be red or is it going to be blue, if I had to predict. Now, nearest neighbor, essentially the outcome, if you were to visualize the outcome, would look a bit like this. So it would say if your point was here, it would be classified as blue. If it was here, it would be red. And again, a thing to note, it makes mistakes. As you can see, that there are green points inside of our red area. There are red points inside of our green area. There's not really much we can do about that. It's always a best guess. It's always a trying to approximate and get as close to the truth as it possibly can. So let's have a look at nearest neighbor and how it works. So the way with nearest neighbor, that if you essentially put something in if you created a point, what it would do is it would try and find the 3 nearest points to it, and it would ask those what they are. So for example, if I was this green circle right now, and I didn't know what I wanted to know if I was a red triangle or a blue square. So I would ask essentially my nearest 3 points and say, I would say, what are you? And in this instance, I can see that 2 of them are red triangles, and 1 of them is a blue square. So I would therefore say, okay, I'm probably a red triangle. That would be my prediction. Now, something that you might note about this is sometimes if all 3 of them were completely different, I wouldn't be able to predict anything. There would be no majority. There would be no consensus, which is why on this diagram, sometimes like over here, so if this, where my red dot is just here, the 3 nearest points, 1 is blue, 1 is green, 1 is red. So it has no idea what that point would be. It can't predict anything. It's called k nearest neighbor because k can be a different value, and you can modify this algorithm. And what the k part is it's the number of closest points that you want to essentially ask what they are. So we were just looking at 3 nearest neighbor when we were looking at this. But when we're looking here, we're actually looking at 5 nearest neighbor. So I would say that, okay, the nearest, out of the 5 nearest points to me, 3 of them are blue squares and 2 of them are red triangles. So therefore, I'm probably a blue square. it can really depend on your use case, and you have to kind of try out different algorithms in order to test which is the most appropriate one for you. So let's have a look at PHP again, and should have this over there. Cool. So if we go through our 4-step machine learning process, again, what's step number 1? Acquire data, yeah. So that's lines 8 and 9. The difference here is because we're classifying stuff. We have our x and y as our point, so 1, 3, and we're saying that is A, or blue, or green, or whatever. So 1, 4 would be A, 1, 3 would be A, 2, 4 would be A, 3, 1, 4, 1, and 4, 2 would all be B. Just to explain that. Step number 2 is train our model. So line 11 and 12, we're just training our model and we're passing it in that data. Step number 3, yep, ask it a question, so we're calling predict. And step number 4, get our answer. Let's see what happens. So in this case, I've given it the point 1, 5. That was the question that I asked it, and it's given me the answer A. Now, I mentioned earlier that sometimes it can be quite hard to visualize in your head if something's right or not without a graph. How unfortunate, we don't have a graph. What a shame. We can also just try something else just to prove to you that it's not just always going to return A. I can try 3, 2. And we can see that that will return B. Now, of course, I do actually have a graph to prove that to you. So this was our training data. We had our A's and our B's. Now, if I add in those 2 extra points, that 3, 2, and the 1, 5, we can see that it matches and they're quite clearly in those clusters. Looking at a graph, it becomes really obvious as to what they probably should be, whereas it can be quite hard to do that just by looking at numbers and trying to work it out in your head. So just to kind of round off, I just wanted to talk about some of the uses of machine learning and why it might be useful for any of you. So if you think about numerical analysis, which is actually what we've been doing a lot in this talk, how could you use that? You could use it for exceptions. So you might, for example, be monitoring like the number of 404s that you get on your website. And you might suddenly see that after a deployment, your number of 404s spike up through the roof. And it might be because, oh, you just removed an asset that was used by your mobile app. So you can actually use this kind of stuff for exceptions and errors in order to kind of see anomalies or differences that you might not expect. If you think about e-commerce, so on Amazon or any online retailer, who's bought something because they suggested you might want to buy it? They've been like, people like you often buy this. Who's bought something like that? Okay, quite a few of you. I think there's something ridiculous, like 8 or 9% of Amazon's revenue is based on things that they suggest that you buy, not on stuff that you wanted to go and buy and went onto the site to buy. That can be a massive amount of revenue increase. So it's definitely worth kind of considering that in sort of on smaller cases. Maybe you want to buy this. You could look at it in fault detection. At my old company, Sam knows, what we used to do is we used to essentially monitor broadband networks for ISPs. And we would then essentially report back to an ISP when there was a problem, and we would also then try and do some root cause analysis to say, okay, there's a problem with your network, A, fault detection, B, that problem is related to router firmware, for example. You might do it for classification. In my current context, in my current job, we classify banking transactions, and we're like, okay, this one's food and drink, this one's groceries. Or you might classify it as a particular merchant. So you might say, oh, this one is Starbucks, or this one is Costa. You can also do some cool stuff with natural language processing, which I haven't really gone into much. But you could do analysis of support queries. So say that you suddenly see an increase of support, increase in customer service questions just after you've done a deployment. Or relating to that feature that you just deployed. There may be an issue there. It may be that your UX isn't particularly obvious. You could also do analysis of large numbers of documents. I was working, a friend of mine was working at a law firm, and essentially what he was doing is working on this, this process that when you go through a litigation, you basically give, or in the UK anyway, you basically give the other side as many documents as you possibly can, so you can't see like the one document that says, yes, I committed the crime. So you just give them thousands and thousands of documents, so they'd have to spend God knows how much money on paying people to read all those documents. Imagine if you could get a machine to read all of it for you in like half a day. So you can also do some cool stuff with analysis there. And finally, it's fun. It can be a really cool thing just to go and have a play. It might be useful to you in your agency or something else. So yeah, just go have a little play, see what it's like, and you might enjoy it. Thank you very much. Have we got any questions? And I'm also told that there is a prize for the best question. Well, I think we'll pass the microphone around just so we can...
How are you deciding which algorithm you should use in?
It really depends on the situation. So sometimes, and kind of, in a lot of times, you might have to try out 4 or 5, just to kind of find the one that matches your use case. If you look at the nearest neighbor, even nearest neighbor itself is the algorithm. There are the different variants, so 3 and 5. So experimentation is basically the answer there. So first of all, looking at your problem space, like am I trying to classify things, or am I trying to discover things, supervised versus unsupervised learning? But then once you kind of get past that, then yeah, it's a case of just experimenting with the available options left for you.
Also, another question.
Go for it.
In PHPML, is there any algorithm for nonlinear regression?
Off the top of my head, don't know. You'd have to double check. It's a nice library. I highly recommend using it for playing with, but it can't handle huge, just to explain like the downsides of it, it can't handle huge amounts of data very well, and also can't handle floating point precision very well. So once you get to quite precise numbers, then it starts to break a little bit. But yeah, it's good for, definitely for playing with and smaller use cases.
Thank you.
Hi, hello for your presentation first. It's Uğur. I just want to ask you, you told that you've been working for a company that creates prediction for financial companies. So is it enough to use regular, directional regression for make prediction on financial predictions? I mean, what kind of algorithms do you use now for your company and for your work?
Yeah, so I mean, it depends on the individual case. When I was at my last company, Sam knows, we did a lot of basic stuff as well as a lot of more complicated stuff. So for sure, we had like stuff doing linear regressions and using things like nearest neighbor for small use cases that might be implemented by individual developers. At my new company, Bud, most of our stuff is artificial neural networks. So stuff that kind of goes a bit beyond what we've talked about in this talk, but is all ultimately still statistics once you get down to it. But artificial neural networks, basically big if statements. Clever if statements. Yeah, there's a question there.
Thank you for presentation. I was wondering that you try to get prediction with 64, am I right?
For what, sorry?
At your demo,
yep.
It was, you asked for prediction, it was 64, am I right? At first demo.
This one?
Yes,
yeah,
64, yeah.
Yeah.
And you got a result, and
yep.
I was wondering that as long as you try to get the same value, I mean 64, you will get always you will get same value and same result. As I recall,
yeah,
yes, it's.
It would always be the same result, because essentially what happens is once you've trained your model, then it will. Sorry, I'm trying to. So once you've trained your model, it generates what that line is, so that a plus bx equals y, and you can actually ask it for to print out what that is. So if I run that, oh, it's an array. So you can actually, so there you can see what the A value is. So the A value is the one at the bottom, the minus 7.9635, etc. one. And you can also see what the B value is, the gradient, or the coefficient as it describes it, which is 0.1873. So yeah, you can actually find out what that line is, and you could then essentially do the question asking stuff yourself if you wanted to.
Okay, got it, thanks.
No worries. Yeah, there's a question there. If you just shout it out and I'll repeat it, because it will be quite complicated for the microphone to get to, I think.
Yeah, okay. Where do you draw the limit to stop using PHPML? I guess there are limits for PHPML. I mean, where do you stop using PHP and pass to something else?
Yeah, so the question there was, why would you stop using PHPML and move to something else? The answer there is generally memory consumption. PHP is probably not the best language to process terabytes and terabytes of data in. There also aren't really algorithms in order to train your model separately in different places and then combine it together as partial trains. Although some of the ones in PHPML do. Also, as a floating point precision, when you need a certain level of, when you do need that certain level of precision, it doesn't handle that for you. Other languages handle it better. If you wanted a language to go a bit further with, you can have a look at Python, or look at something like Pandas or NumPy. But that involves learning a whole new language. So if you're just getting started, then just use PHP and kind of go from there.
Multi-dimensional data, is it supported by PHPML or not?
Yeah, so the question there was, obviously in my examples, I was only looking at two-dimensional data, so X and Y. Would it work with more dimensions, so 3 dimensions, 4 dimensions, 12 dimensions? The answer is yes. If you look there, where it's got an array with a single value, that's because I'm only doing it in 2 dimensions. So I have the target and I have the sample. If I put multiple ones in the sample, it would add more dimensions to it. So we might have 5 in the samples and 1 in the target, at which point it's 6-dimensional.
Another question, please. Should we, sorry, can we predefine the error rate, or
What do you mean, sorry?
For each training model, we try to minimize the error rate?
Oh, right, yeah. So the question there was related to, I think, basically, could we try and make it more exact, more precise,
If we
have
can,
a smaller error margin?
yeah.
You can, by having more data, basically. The more data you have, the better. Any other questions? Yeah.
Thanks for your presentation. I have a question. How you save your model in PHPML? How you save? You create a model, for example, last squares using in here. But how you save? You train, okay. For example, I use PHP. Every requested, each requested, per each requested, train again, or you say model?
Yeah, so the question there is, would you retrain your model least squares object. You can serialize that object and save that, unserialize it, and then get that object again and run your predictions and stuff on it. Or in the least squares regression model, when I just showed you, you could get the coefficients and get the line. You could just store those two values as well, essentially your A and your B, and then just plug stuff into an equation in the future as well. So you wouldn't have to handle serialization and unserialization of objects, which is quite fancy. Any other questions? I think we're a bit behind time, so we one last one as well. Awesome, perfect. Oh, I decided the best question. There's so many. I actually really like your question at the end about how to handle things like performance and efficiency.
How to save your model? For example, if you use Python, you exist without model.
Yeah, so you could serialize that and save the